here are some more integration by parts problems. So here I've got 2x secant squared of 3x, and it seems reasonable, right? Again, thinking about the late acronym. Don't worry, we'll get to a problem where we let u equal the trig function. God, my hair looks wild. Sorry. U is going to be the algebra thing. You could put this 2 out in front. It doesn't really matter. Yeah, I don't really care. I might. Yeah, let's just go. Let's roll with it. Let's let u equal 2x, and then dv. Now the reason why dv is an okay choice for secant squared of 3x dx here is that we know how to integrate secant squared. Right? The antiderivative of secant squared of x is just tangent of x, because the derivative of tangent of x is secant squared of x. So du is going to be 2 dx, and v, the antiderivative of secant squared of 3x, is going to be tangent of 3x, but not quite just that, because the derivative tangent of 3x would be secant squared of 3x times 3. We have to divide by 3 to account for the 3 we get from the chain rule. Okay, throw it in the formula. Ultraviolet super voodoo. It's fun to say. So this times this. So 2x times tangent of 3x divided by 3 minus the integral of v du, which is tangent of 3x divided by 3 times 2 dx. Okay, so I'm going to rewrite this as 2/3 x tangent of 3x minus 2/3 the integral of tangent of 3x. Okay, how do we integrate tangent of 3x? You guys might have talked about integrating tangent of x in class and shown that it's the natural log of secant, or the negative natural log of cosine. I might have gotten this backwards, not right. So here's how you integrate tangent. You write it as sine of the cosine. So sine of 3x over cosine of 3x. And then you do a u sub. So I'm just going to do this part on its own. So if I let u equal the denominator, the derivative of cosine of 3x is negative sine of 3x times 3. So I have du over 3. Let's make it negative du over 3. So I have the dx down there. Equals sine of 3x dx. So rewriting this integral, right? The integral of sine of 3x over cosine of 3x dx. This sine of 3x dx becomes the negative du over 3. So this becomes the integral of negative 1/3 du over cosine 3x, which is just u. So it's negative 1/3. The integral of du over u is the natural log of the absolute value of u, which is negative 1/3 natural log of the absolute value of cosine 3x. So whenever you're integrating tangent, if the integral of tangent of x is negative natural log of cosine of x, the integral of tangent of 3x is negative natural log of cosine of 3x divided by 3, just like we always do when we have that kind of thing. Here's what we get. We get 2/3 x times tangent of 3x minus 2/3 times negative 1/3 natural log of the absolute value, yes you need it, of cosine of 3x. Let's see. And then I would distribute the negative 2, I would multiply this and I'd get positive 2/9. So let's actually just do that real quick. So negative 2/3 times positive 1/3 is 2/9. Sorry, negative 2/3 times negative 1/3 is positive 2/9. Natural log of cosine of absolute value. Natural log of absolute value of cosine of 3x. This would be our answer. Yeah, you can totally factor out the 2 like you could have factored out the 2 in the beginning. Let's see what our time was here. Yeah, we can do the other problem on the other side. So let's look at this other problem I've got here. This one is kind of interesting as well. Looks like integration by parts, and it is. But the problem here is, if I let u equal x to the 5th and dv equals e to the x to the 3rd, there is actually no way to anti-differentiate e to the x to the 3rd. It's un-anti-differentiable. It's called, oh, there's a word for it. I don't remember what it is. So since I don't know how to do this with integration by parts, I'm going to kind of fall back on my usual method of attack, which is, can I do a u sub? Well, yes. A good choice for u would be x cubed, because x cubed is stuck inside the exponent here. The du is 3x squared dx. I'm not doing integration by parts yet. I'm not finding v and dv and all that. So then I don't have, well, let's see. I do have an x squared dx, right? Because I have an x to the fifth. So I could rewrite this as, this is x cubed times x squared, where x cubed times e to the x cubed lives out front, and the x squared is going to get grouped with the dx. And if I do this, 1/3 du equals x squared dx, well then I can replace x squared dx with 1/3 du. So the integral ends up being, so x cubed, well actually let's do this part first, right? That's my 1/3 du. And then x cubed times e to the x cubed, each of those x cubes can be replaced with a u. And this is where I'm always like, I should use a different letter, because now I'm going to do integration by parts and I don't like using u with u already. So let's go back and actually change all of our u's to t's, just so that we can then do a nice u substitute, u integration by parts. So t equals x cubed, dt equals 3x squared dx, 1/3 dt equals x squared dx. And then this is the integral of t e to the t dt. And now it's definitely an integration by parts kind of problem because I have my variable like x to the first or t to the first times e to the t. So I'm going to let u equal t, right, the algebra part. dv is going to be the rest. And then du is 1 times dt. And v is e to the t, because the antiderivative of e to the t is e to the t. So rewriting this is going to be 1/3 times u v, which is t e to the t, minus the integral of v du, which is e to the t dt. Integrating, I get 1/3, I still have t e to the t, minus the integral of e to the t is e to the t. And instead of writing the brackets, I'm going to distribute the 1/3. So it's 1/3 t e to the t minus 1/3 e to the t. Let's see. And then lastly, I plug back in that t is equal to x cubed, and I get 1/3 x cubed e to the x cubed minus 1/3 e to the x cubed plus c. So that's an example of a u sub and an integration by parts in one problem. All right.